With that, we're going to move on to John Englander, and his talk is on melting glaciers and rising seas. John is president of the Rising Seas Foundation. He's a very well-known author, really puts, I believe, into perspective, not what might happen, but what will happen. And with that, John, please.
Thanks, it's a pleasure. And it's great to follow on the two previous presentations, which both talk about climate change and the varied kinds of effects we get, including flooding. I'm going to build upon that and clear up some confusion that's widespread, not just in this audience, but worldwide as we talk about flooding as a climate impact. For those that like to tweet, either want to communicate, that's my Twitter handle @John Englander. We're seeing more and more cities, not just the iconic Miami shown here, with incredible development amidst water on all sides. But of course, we all are left with images. Some is just shown earlier in presentations this morning. This was Superstorm Sandy, showing how homes and communities will be breached by extreme storm events. I like to talk to each audience in their own vernacular and idiom, I guess. And for you, it's obvious to talk about diagnosis and prescription or treatment. And we don't often think of it that way, but it's one of the things that excited me about being invited to talk to this audience about public health and emergency medicine. This is the oldest house in Broward County, Fort Lauderdale. For some of you might be familiar, it's the Stranahan House. It was built 100 years ago, actually a little over. When that house was built, and until the last few decades, the dock didn't go underwater. Now, this is not permanent flooding. This happens at extreme high tides, which in Florida are now called sunny day flood events. In other words, there's no storm system, there's no hurricane, there's not even a low pressure system. It's just when the extreme tide cycle, tides vary, daily and monthly with new moons, and then there's a 18.6 year progression of tides. So when there's an extreme high tide, the dock and porch of this house are now underwater in clear skies. And that's because of sea level rise showing up as high tides. Showing you a more modern context, I love this slide. A friend of mine took it. There's a truck off to the right indicating this is a street here in a residential neighborhood. In the background, there's boats. There's a canal here. And they keep a no wake sign available to put up on the street. Anybody who's done boating knows you're not supposed to throw a wake in a crowded area of marina because the wake will cause disruption to other boats. Well, here they have a no wake sign on the street, and they put it up whenever there's a peak high tide. This didn't used to happen 30 years ago. And the problem is that sea level's rising. And again, it makes the extreme high tides higher. As soon as the water dissipates in 3 or 4 days, they take that sign down because they don't really want to have it known that their community floods regularly, because if somebody wants to go sell their house, it's really not very helpful to have a no wake sign on the street, which begs the question of how often the flooding happens. I want to talk to you about 3 things that are both facts and sources of confusion in the inverse, starting about climate change and global warming. We'll call it either one you wish. In the previous 2 speakers, they referred, of course, to the issues of greenhouse gas emissions. We sometimes call them carbon emissions. By the way, that's a very confusing term. Carbon in the air is black smoke or soot, and we try and keep that out of the air for air quality. But unfortunately, the scientific community has used it as a shorthand for carbon dioxide, a perfectly clear gas. That's like thinking that water is hydrogen and oxygen, the elements that make the compound. So, while I don't pretend to think we're going to get the world to stop calling greenhouse gases taking carbon out of the air or stopping carbon emissions, it really is part of terrible communication. And one of the reasons we're not communicating well to the public, because we keep talking about taking carbon out of the air when we're really talking about taking a clear gas out of the air, and also keeping carbon out of the air as for air quality and respiratory effects. So just an example where communication matters. And unfortunately, we're doing a terrible job as a society communicating the problem distinction between air pollution in the form of particulate matter and changing the atmosphere and its heat retaining qualities. But anyway, that's not for today. There are three largely separate issues. We do need to reduce greenhouse gas emissions, sometimes called sustainability, so that as we make energy, we don't make the planet warmer. Absolutely imperative. And that was the main discussion at the recent COP26 meeting that the two predecessors mentioned. We also need to be resilient to the kind of things that are happening today. And I'll get into that a little bit, the storms and heavy rainfall and other effects, wildfires, droughts, all of the things that we're seeing and are reported in the headlines year by year at the moment. So we need to improve that resiliency. And the previous speakers referred to adaptation and resiliency, and both are important, but they're different. Adaptation, at least in my vernacular and explanations, is what do we need to plan differently for things which we know are going to happen and go way beyond resiliency. And sea level rise is one of those factors, which we'll dig into a little bit. The second issue that I want to clarify is that we talk about coastal flooding. It's intuitive and normal to talk about flooding as if it's one kind of thing. Well, that would be like saying somebody's sick. Of course, it's not enough information to treat them. We have to separate coastal flooding into the weather events of a storm like a hurricane, heavy rainfall, and as was mentioned this morning, we're continuing to get record-breaking rainfall. And that's because the warmer oceans are evaporating more. And if there's more moisture in the air, it has to come down as rain or snow. That's confusing because we're also getting more drought in a warmer planet. But so we get flooding from storms or low pressure systems even, heavy rainfall in a location, and we continue to break those records. And then runoff, where the rainfall multiplies downhill or downstream. In other words, you could get 6 inches of rainfall in a day, but you could get 3 feet of flooding from runoff due to the topography, or even a lower street in a fairly flat city. Down in Miami, which doesn't have much elevation, but the water will go from a high street to a low street. So I like to say that the flooding from weather events is storms, rain, and runoff. And then, as I showed you some images already, extreme high tides, whether you call them king tides or spring tides or perigean high tides, the more proper term. The tides are, of course, determined by the planetary positions, the pull on the oceans, and they're very predictable, and they're independent of weather. They seem to get higher, but that's because of the next issue, rising sea level, my specialty. And then along with those 5 kinds of flooding, there's coastal erosion, which widely by convention is somehow confused with flooding. And you can understand why, but erosion is a natural process on the shoreline. Any shoreline of sandy beach will have erosion and deposition on the other side of a jetty and so on. But erosion happens in extreme cases during storms, but erosion even on a perfectly clear day is happening grain by grain along the beach. And it's different than flooding, actually, but again, it's easy to see why we confuse it. But in terms of conceptualization and communication and educating others, it's useful to just make that distinction. And the third and final kind of confusion I want to clear up this morning is about rising sea level. And the 5 bullets I would make to you to start are, one is it's accelerating, and that's going to surprise us, just like the pandemic. It's unstoppable, regardless of what we do to slow greenhouse gases at this point. It's generally unpredictable, which is surprising, and I'll demonstrate that in a minute or document it. It's essentially permanent. Sea level is not going to go down for thousands of years, but higher sea level makes flood events worse. So it has a duality. And the biggest problem is it's slow, like a drip filling a bucket. And although we talk about it when we talk about storms and rain and so on, sea level rise is different because it's only rising at about 1/4 of an inch a year right now. And that's essentially irrelevant in the scheme of the 10 or 20 feet of flooding we can get from storms and the other causes. You've heard about the UN IPCC this morning, the Intergovernmental Panel on Climate Change, that for 3 decades has been putting out reports every 6 or 8 years documenting the status of the climate. The recent report, the 6th assessment, sometimes shorthanded as AR6 for Assessment Report 6, came out in August. And that scientific finding by thousands of scientists globally in a very highly documented process led to COP26, which is the Conference of the Parties, the 196 nations that agree on policies to deal with the science. And I think that's clear, but it's just useful to sometimes, separate those two things. Now, to be really simple about it, the goal, as both preceding doctors mentioned in their comments, is to keep the warming to 1.5 degrees Celsius, 2.2 degrees Fahrenheit. Now, confusingly, that starts with a baseline of pre-industrial, so about 200 years ago, before we started burning fossil fuels in great quantities and changing the atmosphere. We've already warmed 1.2 degrees since pre-industrial era. So the goal from COP was to try and limit the warming to another 0.3 degrees Celsius, and in a worst case, to keep it at 2 degrees, another 0.8 degrees Celsius. And you can sort of double the Celsius for those to Fahrenheit, if that makes it easier for you. But here's the thing that hardly anybody's paid attention to in all of our concern and enthusiasm for what came out of COP, is the proposals made at the COP meeting in Glasgow only keep the warming to 2.4 degrees. At present, we're on the path to 5 degrees of warming. But even if we could achieve the 1.5 degrees by some magical technology and changing our behaviors, that's 20% warmer than we are now. In other words, we're at 1.2 degrees, and they're saying that if possible, we should try and keep the warming to 1.5. That's considerably warmer than we've been for the last 50 years. More ice is going to melt. We're going to see more effects, more storms. So it's not to depress us, but it's reality. It's like a patient that we know has either terminal illness or something that's chronic, or that is near the end of life by natural causes. You deal with those realities of life all the time. We need to think of the planet that way, that we have to try and slow the warming. What came out of the COP conference as an agreement is okay as far as it goes. But even if we could achieve its goals, we are going to be worse off than we are today in terms of the climate change impacts, which I actually prefer to call global warming, by the way, because of this temperature profile. Okay, sea level rise. Let me dig in and clarify some of the confusion here. This is NOAA's latest national projection for the United States. That's, of course, the National Oceanic and Atmospheric Administration. I have high regard for them. They're excellent scientists. But this chart, which they're about to update probably next month, shows projections for sea level rise. Most people think it's informative. It's not. In fact, it's informative in a negative sense. It's showing between now and the year 2100, the next 8 decades, that sea level rise could be somewhere between 0.5 meter and 2.5 meters, 1.5 feet to 8 feet. Those are straight lines. It's similar to somebody 2 years ago saying we've got a pandemic called COVID. And we don't know what the trajectory will be because there's just too many variables. But we're going to plot out 6 lines. That doesn't tell you much. It may help you think through how many hospital beds to ready, or how many vaccine doses to prepare, or how many respirators and different things. But it's not saying that it's going to follow any one of the lines. And that applied to the pandemic, and it applies to sea level rise. But in fact, if nothing else, the spread between saying sea level rise could rise between 1 foot and 8. Okay, tell me something I can act upon. So here's a chart. It's in my book, which I'll put up the name at the end there again. I think I had it on the title slide, Moving to Higher Ground. But this was done with Dr. James Hansen, one of the most famous climate scientists, for my book. And it shows 400,000 years to give us a big picture of climate. And many scientists now use this slide, and you're welcome to use it. In fact, if you get my book, it'll tell you how to download it. It's also on my website. That the green line is carbon dioxide, a greenhouse gas. The red is global average or global heat level, and the blue is sea level. So it shows the correlation between the greenhouse gas of carbon dioxide, global temperature, and sea level. And as you can see, over 400,000 years, there's been a regular pattern. The three lines move together. The peaks are rather evenly spaced between 95 and 120,000 years. So call it roughly 100,000 year cycle. It's about an 80% down and a 20% up on each of the lines. And the peaks line up perfectly. And for 2.5 million years, this has been going along just fine by nature during the period we call the Ice Age cycles. And in fact, it shows on the red line, the last Ice Age cycle was about 20,000 years ago. The peak, I should say, the glacial maximum. We've been in a period called the Holocene, as shown in that other reverse block there of a label. The Holocene has been 11,000 years of fairly stable climate. And as the planet warms, the ice sheets melt, which we'll get to in a moment, the glaciers. And when the glaciers and ice sheets melt, sea level goes up. So there's an obvious correlation between the red line and the blue line. When the planet's colder, the ice sheets grow over thousands of years and sea level eventually falls. And when the planet's warmer, the ice sheets on land melt, as I'll show you, and sea level rises. The relation between carbon dioxide, the green line and red line, is a little less obvious. Historically, when the planet has gone through the ice age cycles by nature, without human intervention or effect, when the oceans are warmer, they release carbon dioxide. When the oceans are colder, during the cold phase of the ice age cycles, the oceans absorb carbon dioxide out of the atmosphere, or carbon dioxide dissolves into the ocean, effectively lowering the level. And that's been a natural cycle again. But then here along come humans a few thousand years ago, 100,000 years ago, and in the last 2 centuries have been changing the atmosphere. And you can see that is circled in the upper right. Carbon dioxide has left the range of 180 to 280 parts per million and is now at 415 parts per million, as shown in that dotted circle or dashed circle. And the problem is that carbon dioxide was demonstrated to trap heat. And so while carbon dioxide levels, the greenhouse gas will rise when global temperature changes, there's a separate forcing function that carbon dioxide traps heat, was proven in 1859 by Dr. John Tyndall, and is easily replicated. And we know that carbon dioxide is a clear gas, perfectly clear, but traps heat, radiant energy, and has an effect to warm the planet. And the problem is that over thousands of years, these 3 lines move together. And the green line is shot up vertically like a rocket. And the red line is starting to follow, and the blue line is starting to follow temperature as the ice sheets melt. So this graph shows a couple of things. One is there was a natural climate cycle. It's been going on for millions of years, actually 2.5 million years of ice ages in a regular repeating pattern. And we probably would have been entering the next cooling phase, 80,000 years to the next cold spot. But we've changed the atmosphere, so we're trapping more heat. Now, the problem is, of course, seeing that these 3 lines move in lockstep over centuries, is that it's very clear that with carbon dioxide way above norm and that it traps heat, it's going to raise the planet's temperature, which will melt ice, which will raise sea level. So that's the big picture. And again, you're welcome to use it. It's the first graphic in my book. Other presenters this morning have already reminded us what hurricanes are. We all know what hurricanes are, and that's a good phenomenon for everybody in the world, I guess, to think about the effect of storms. But hurricanes are getting worse, probably because of more heat in the ocean, which is the driving force for hurricanes. Sea level rise is a different function, and the two locations from Greenland at the top, the white, to Antarctica at the bottom, that ice on land represents 98% of potential sea level rise. The Arctic is warming 3 times faster than the global average. We worry about the polar bear, but setting that aside for the moment, and although not to diminish it, but as we go from bright white ice to dark blue ocean, we're absorbing more heat. And it's these icebergs which kind of are evidence of that. But as another point of confusion, most people think that melting icebergs add to sea level. They don't. Like ice cubes in a glass, shown here in this little image, just to help clarify the science part of it. Ice that's floating protrudes about 10% above the surface. But as ice melts, whether it's floating ice cubes in a glass as shown there or a giant iceberg, as it melts, it doesn't change the water level because ice is about 10% less dense than water. That's why it sticks up. And so as it melts, it basically compresses, if you will, in volume, or reduces in volume. So melting floating ice has no effect on sea level, even though most people think it does. It's the ice on land, the glaciers, back to my talk title, or the ice sheets at the center where the glaciers emanate from. But as the ice on land either melts and the water gets to the sea, that raises the level. That's like pouring more water in our glass. As the glacier breaks off or calves into a new iceberg, that's like adding an ice cube to the glass. That, of course, raises the water level. The third effect that causes global sea level change is thermal expansion of seawater. As the oceans warm, they slightly expand, but that's a minor effect compared to the ice on land. There's enough ice on land between Antarctica and Greenland to raise global sea level 212 feet, 65 meters. About 7 parts of that are in Antarctica, and 1 part of that is in Greenland, but Greenland's melting faster. Now let's bring this home to kind of the practical place or issues for you as in emergency medicine and public health. First of all, let's be clear that in terms of areas that are going to flood, just a meter, about 3 feet of sea level rise, will put key areas of Florida, just as one example, underwater. But there's 140 nations and 24 states in the United States that have a marine coastline. They're all going to be affected. This isn't just a Florida problem. There's large parts of Florida that will be fine, even at 10 feet of sea level rise, 3 meters. Orlando's 80 feet above sea level, for example. Gainesville's 100, double that, 160 feet. But to make the case for why sea level is so profound, that's what Florida looks like today. 20,000 years ago, during the last cold period of the Ice Age cycle, sea level was 400 feet lower, so Florida was twice the size. And 120,000 years ago, at the last warm spot in the Ice Age cycles, sea level was 25 feet higher, and Florida was half the size. That's because, just to use the funny cartoon from the Ice Age series, we had 2 miles of ice, 10,000 feet of ice, 3 kilometers over the northern hemisphere. As that melted, sea level rose 400 feet. We can see that in a very simplistic graph that, again, is in my books and on my website. But since the last ice age, sea level rose 390 feet, call it 400 feet. That's about 30 floors of a building. It did not rise smoothly. It will not rise smoothly in the future. Like the pandemic, there will be bursts of activity. And here you can see there were 3 steps when sea level rose more than 10 feet in a century. It's happened before, and it will happen again. Sea level, since we had tide gauge records, has risen about 10 inches in the last century or so. But although it's hard to perceive it here, the line is getting steeper. And I'll take that little red line there, the last 30 years since we've had satellite data, compared to the tide gauge records shown in this larger graph since 1850. And what's happening now that we have really precise, less than a millimeter resolution of global sea level rise, is it was 1.5 millimeters a year. That's about a 20th of an inch. Then since the year 2000, it's been about 3 millimeters, double that. And now in the last decade, it's almost 5 millimeters a year. Like looking at the pandemic, this should get our attention. This shows an acceleration. Now, 5 millimeters a year is only about 1/4 of an inch. By itself, that's not the problem, but it's like the trajectory with the pandemic. Where's it headed? So when we go back to the graph I showed you a minute ago, as I begin to wrap up here, we can see the pattern. There was natural climate change, there was natural sea level rise, there was natural response to what we think of as the ice ages, changed the carbon dioxide level. Now the carbon dioxide level is changing temperature, which is melting ice and raising sea level. We've never seen this in human history. The last time sea level was higher, as shown there on the blue line, was 25 feet higher, was 120,000 years ago. We have no cultural memory of that. We need to be analytical about it. So I believe in, as I wrap up my part of this program to bring you this external input, I guess, but I really appreciate the opportunity to both provoke your thoughts and inform you and work with any of you. As disaster medicine and public health professionals, you have an opportunity to educate and lead in your community by your role. And in particular, you can explain when plans and facilities are off target because people are confusing storms, a weather event, heavy rainfall, a weather event, high tides, a rather predictable change, which is changing because of sea level rise. And then what could happen with long-term sea level rise? But again, with only 1/4 of an inch or 5 millimeters a year right now of sea level rise, it's irrelevant almost. In the next year, we do not have to worry about sea level rise. We have to worry about a storm as an effect of climate change and a warming ocean. We have to worry about heavier rainfall and runoff as effects of climate change. But sea level rise in the next year, the maximum is a 1/2 inch, relatively small compared to the 10 or 15 feet of flooding you can get from those other things. But over the next 30 years by mid-century, or the next 80 years by the end of the century, we could have 5 or 10 feet of sea level rise. So that requires planning differently. Because as you know, hospitals and infrastructure are designed typically for 50 to 100-year useful life. So like a physician looking at a patient who has a known terminal illness, you can advise them and their family to take certain steps appropriately, both to improve the situation and also to be prepared for the inevitable outcomes. Climate change has many impacts. We are likely to see more disaster flood events, which are short duration flooding. We must slow warming, which means energy efficiency and renewable energies are very important. What we think of as sustainability. We should plan for resiliency, dealing with floods, fires, droughts, and heat that are all part of the future. And we should plan to adapt to rising sea levels, which are largely unstoppable and unpredictable in terms of precise levels and timing. We should encourage and distinguish other green efforts like recycling and things like that, which are wonderful, but have nothing to do with slowing climate change or sea level rise. There are things we can do architecturally. This is a city in Hamburg, Germany, that I visited, where they have regular severe flooding because of a phenomenon, but it's caused them to design to live with rising waters, both short-term and long-term. And to close, we don't have a choice to deal with sea level rise, just like we don't have a choice to deal with the pandemic. The sea is rising for the first time in human history. After 6,000 years of relative stability, sea level is now on the march upward, having broken out of the natural climate cycle of the ice ages, when sea level would have been starting to fall for the next 80,000 years, but now is rising. We should try and slow the warming. We should be prepared for the public health impacts, the emergency events from greater storms, but we need to recognize that sea level rise is part of our future, and we need to take it seriously, thinking about our loved ones and generations to come. Those are my contacts. If anybody wants anything further, my new book has been out for about 6 months, getting well reviewed, but Dr. James suggested I put it up here as a just for your awareness, and those are other ways to contact me. So thank you.